Let me share my screen. Okay, so we were about to begin the discussion. And again, I thank you all for waiting since I had a power issue and got knocked off the internet. But we were beginning to discuss the second version of the central limit theorem, which is related to the sum. So again, it really says the same thing that we had before, but instead of looking at the average or the mean, we look at the sum. So if you took the last four digits of my social, again, 6275, we would simply add them together to get the sum. Sum implies that we add. So my sum would be 20. For my daughter, her sum is 11. For my husband, he would be, let's see, 9, 17, 23. Okay, so we're looking again at, instead of the mean, we're looking at the sum. Again, with that idea of a large enough n from an unknown distribution, and create the histogram of those sums. That resulting histogram will have an approximately normal bell shape. Again, the idea of what's large enough kind of depends on the original population. We tend to use the magic number of 30. But again, if you're really, really totally different from a normal distribution, then you probably want to have a larger sample than that. And again, we do sample with replacement, which means you would select it, record it, put it back. Choose another one, record it, put it back. And the results for the central limit theorem for the sum has the following parameters. The mean of the central limit theorem sum is equal to the n, or your sample size, times the original mean. The standard deviation is the original standard deviation times the square root of the sample size. So there's still a direct relationship between the means and the standard deviations, whether you for the unknown and applying the central limit theorem. But again, the main thing that comes out of the central limit theorem is that I can force any distribution to be normal. Again, I walk through the example again of our last four digits. And again, remember, we talked about this earlier, but this original, if we look at each individual digit, so I had 131 digits, or 131 people with four digits. So we had 524 digits. We have a uniform distribution. This is the same example we had earlier. So this time, instead of looking at the average, I looked at the sum. So I added together the four digits and I graphed those sums. When you graph the sums so that I had 131 sums, again, what we get is a normal, or a reasonably normal distribution. And our mean this time is about 17.9. 17.9 should be roughly our sample size times the original standard deviation. So our sample size, we had 4 in each group, and the original mean was, I have to go back and get it, 4.45229, okay? So we had 4.45229. So if I multiply those, and again, I might be slightly off, but again, it's an estimation. I do actually get 17.80916. The standard deviation is the original standard deviation times the square root of n. So I would have, I believe it was 2.897156 times the square root of 4. So that would actually be 2. So 2.897156 times 2 gives me 5.794312. Again, I'm slightly off, but it's an estimation and I'm within the ballpark. So even if we look at the sum of each group, we still end up with a normal distribution. And again, the numbers do compare. It's just a different formula for the mean and the standard deviation. Now, before we look at an example, I want to mention something to you, and then we're going to do an example. Okay, guys, when you're looking at these normal distribution problems, you're going to have to be very, very careful. You're going to have to read carefully. Remember, in the problems that we looked at on Monday, it told us that we had a normal distribution or it was normally distributed. And the other thing with those problems, we were looking for we were selecting a or one individual. At that point, you're not going, for those type problems, you're not going to apply the central limit theorem. So if you're thinking about your homework, okay, on quiz 4, which is the quiz for the normal distribution, you're not going to apply the central limit theorem. You're going to use the mean and the standard deviation that you've been given. If you're being asked to find the probability of a sample mean, and typically you will have maybe an unknown distribution, then you want to apply the central limit theorem for the mean. Now you're going to see those type questions, at least initially, on quiz 5. Now you'll see both kinds on the midterm, and you'll have to decide which thing to use. So that's why I'm trying to point out the things to look for. And then you could also be asked, if you're asked to find the probability of a sum or possibly a total, you're going to use the central limit theorem for the sums. Again, typically here you will have an unknown distribution. The other thing I would point out, typically for these last two, you're going to be selecting a group of items, not just a single. Okay, so you need to pay very close attention to the phrasing in the questions. Okay, you're going to have to read, and you have to read deliberately and carefully, and think about what you're being asked and what information you're given. Okay, so I'm going to go back over to our examples that I put on the Word document. Whoops, wrong one. Get rid of that one so I can. Okay, so here's the example of the sums. Okay, so let's look at how these questions are worded. It says an unknown distribution has a mean of 90 and a standard deviation of 15. A sample size of 80 is drawn randomly from the population. Now, this particular problem, the way the questions are worded, notice how it actually tells you to use the central limit theorem for the sums formula. So it's telling you which one to use. If it did not tell you which one to use and you had to make that decision on your own, a couple of things jump out at me. It says it's an unknown distribution. I have a sample of size 80. And then when I get down here to the questions, it says find the probability that the sum. Okay, so again, the fact that I have an unknown distribution is one clue that I want to apply the central limit theorem. The wording of the question about probability of the sum tells me I want to apply the central limit theorem for the sum or for the sums. But again, this question is worded nicely because it explicitly tells you to use that formula. Now, for the midterm, you're going to be able to have a note sheet. You get one 8.5 by 11 sheet of notes front and back for the midterm. I believe that's right. And so you will need to write down the formulas. Okay, the formulas are not given on the test, so you'll need to write them down. So for sums, the mean for the sum is the sample size times the original standard deviation. So in this problem, my sample size is 80. And the mean given in the problem is 90. So 80 times 90 is 7,200. So the mean that I need to use is going to be 7,200. Again, it tells you here when you're thinking about the standard deviation of the sum. Okay, again, it's telling you to use that formula. But again, I've already given you clues on how to decide which one, what to use if you had to. The formula for the standard deviation of the sum is the original times the square root of the sample size. So in this problem, I would have 15, because that's the standard deviation that's given to me in the problem, times the square root of 80. And I'm definitely going to need to use my calculator for that. Okay, so I have 15 times the square root of 80. Okay, and I get 134.1640786. I would likely, it doesn't indicate here, but I would probably round to 3 decimal places. It should indicate. This one I wrote and didn't put it in there. I apologize. So again, what we have determined is that even though we initially had an unknown distribution, by applying the central limit theorem for the sums, I now have a normal distribution that has a mean of 7,200 and a standard deviation of 134.164. I was mentioning as my power went out that I have not ever experienced or seen the central limit theorem for the sums used. I am more familiar and have seen the central limit theorem for the mean used. And that's not to say that the sum version is not useful. It's just in my experience, I've not seen it used a lot. So that's why we do look at both versions, because in some cases it might be easier or better to use. So if we look at these problems, again, we now know, even though the original distribution was unknown, we now know that it's normal, and we have the mean and the standard deviation. So the first question says, find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. So again, if I'm thinking about my graph, I know I now have a normal distribution. I know that the mean of the sum is 7,200. I'm asked to find the probability that it's more than 7,500. More than would be the region or the area to the right. So notice, again, I'm out here on the right-hand side at the end of the curve. This would be a right tail. So again, I'm using the normal distribution. So I'm going out to Minitab. Same keystrokes. Graph, probability distribution plot, one curve. We want to view the probability. Double click. It is normal. Our mean is 7,200. The standard deviation is 134.164. Whoops. I go to options. It is a specified X value. It is the right tail, and it was 7,500. And I click OK. OK. And it gives me the graph which has the answer. Okay, again, what you're looking for here is this value that's kind of hanging out above the red. So it's 0.01267. So this red shaded region is 0.01267. Now, most times, guys, you're asked to round to 4 places. So if you were to round that value to 4 places, the 6 is in the 4th place. The 7 is next door, so it gets bumped up. So this would be 0.0127. So what that means, what are we doing? The probability of the sum. It doesn't even really give us a variable here. So we would say the probability that the sum of the 80 values is more than 7,500 is 0.0127 or 1.27%. Again, this is the decimal, and we convert the decimal to a percentage by doing the decimal times 100%. Okay, this is the decimal. And that's usually the answer you're going to give if they ask for the probability. If it asks for a percentage, then you would convert it to the percentage. Okay, let's look at another one. Again, we know, because we've applied the central limit theorem, that our distribution is normal with a mean of 7,200 and a standard deviation of 134.164. This question says find the probability that the sum, again, if you were having to try to figure this out on your own and you see that word sum, again, that's the clue that you're going to apply the central limit theorem for the sum. So I know that I have a normal distribution. The mean of the sum is 7,200. And let's say we want to be less than 7,000. Less than 7,000. Less than is to the left. Okay, so because it's to the left, less than would be a left tail. We go out to Minitab. Graph. Probability distribution plot. One curve. We want to view the probability. It is normal. The mean is 7,200. The standard deviation is 134.164. Go to options, specified value. This time we're in a left tail. We want to be less than, and we want to be less than 7,000. I click OK. Click OK. My graph does appear. I'm going to copy it over to my paper. Okay. So again, you're looking for this value that's kind of hanging out in space above this red shaded region, which is 0.06802. So we get 0.06802. Again, typically you're asked to round to 4 decimal places. Again, if we do 4 places here, there's a 0 in the 4th place. 2 is next door, so nothing happens. So we would round this to 0.0680. So the probability the sum of the 80 values is less than 7,000 is 0.0680 or 6.8%. Okay, I think I have one more. Again, we see the word sum. Find the probability that the sum. So again, that's my clue that I want to apply the central limit theorem for the sum. When we do that, we find that we have an approximately normal distribution with a mean of 7,200 and a standard deviation of 134.164. So I'm going to draw the picture. I know I have a normal distribution. My mean for the sum is 7,200. We want to be between 7,100 and 7,600. So we have a between. Mini tab refers to that as middle. We go out and put the numbers in. Because I hope you won't overthink this. Okay, so we have graph, probability distribution plot. We're going to view the probability. Again, it's normal with a mean of 7,200, standard deviation of 134.164. Options, we want to be between, in the middle of 7,100. Remember, you always put in the smallest value first and then the high value. So between 7,100 and 7,600. And I click OK. And I click OK again. Excuse me. And then we get our graph. Again, what you're looking for is this decimal value that's kind of hanging out in space over the red shaded region. So I have 0.7705. So this red shaded region is 0.7705. So the probability that the sum of the 80 values is between 7,100 and 7,600 is 0.7705 or 77.05%. Questions?
There's no need for rounding this one?
No, because you have 4 decimal places. The previous two, Nana, I had to round them because it gave me 5 decimal places. And normally for probability related to a normal distribution, we do 4 places.
Okay.
So that's why I rounded the previous 2 problems, because normally it's 4 decimal places.
Okay.
Other questions?
No more questions.
Okay. So that finishes the central limit theorem. So quiz 4, which covers normal distribution outright, and quiz 5, which covers the central limit theorem, are due by Sunday. And again, I tried to point out kind of the differences in the phrasing so you'll know when to use which one. For quiz 4 and quiz 5, they're separate. But again, when you get to the midterm, they're going to be all mixed together. So watch for those words. Look for those key words. So I'm going to go ahead and I want us to begin looking at the next lesson. We'll be a little bit ahead of schedule, but that's not a big deal because at some point we may get stuck on something. And so I want to go ahead and do the introduction. We have about not quite an hour left to the next lesson within module 2. So let me go back over here to module 2. Oops, I'm not in the thing because I got knocked off. Let me get back into the class. Okay, so we're still in module 2. And I'm going to move now into confidence intervals and sample size estimation. Okay, again, we'll be a little bit ahead of schedule, but with I know spring break is coming up, and that kind of thing. I will tell you that mini project 2 is related to this idea of confidence intervals. Okay, I will tell you that mini project 2 is related to confidence intervals. Okay, so there is a video about the overview of the confidence intervals, but I'm going to try to walk through some of that today before we actually jump into the problems. Okay, so that's where we are. So I'm going to go over to the PowerPoint for confidence intervals and sample size estimation. But before we get into that, I want to kind of make a connection between things that we've talked about previously and where we're headed with this discussion of confidence intervals. Okay, so I'm actually going to do some notes here, and again, I'll share these with you so you'll have them. I honestly don't remember right off, okay, but I know in statistics 1401, and it may have been a while since you took that, so let me review this. In the world of statistics, there are two different branches or two different areas of statistics. One is we refer to as descriptive statistics, and the other is what we call inferential statistics. In the world of descriptive statistics, and if you'll notice, the word descriptive is the adjective form of the word describe. So in that area of descriptive statistics, we are simply describing the data set. You are basically simply stating just the facts. You're making no assumptions whatsoever about the data. The descriptive statistics includes those tables and graphs that we talked about at the very beginning of the course, that data visualization. It also includes that area of descriptive statistics where you're able to calculate your mean, your median, the mode, the range, all of those descriptive statistics, those measures of center, mean, median, mode, measures of variation, range, standard deviation, variance, your measures of position, whether it's the percentiles or quartiles. So that's the area of descriptive statistics. And when we began calculating those statistics, that mean, median, mode, range, and so forth, we were calculating a single value for that measurement. Whether it's the mean, the median, the mode, the range, we were calculating a single value. In statistics, that idea of using a single value is a point estimate. But guys, here's kind of the challenge of using that point estimate. That point estimate is a single value, and you are hedging your bets that that single individual point estimate is the actual correct answer. It's like you are aiming at a target, and if you're going to get to the bullseye, or that point estimate is like you have to hit the bullseye every single time. Okay, so using a point estimate is like hitting the bullseye every time. And so sometimes if we have maybe some of those outliers or something, just, an unusual set of data, our point estimate may not be accurate. We may not hit the bullseye. And we often use those point estimates to approximate the value for the population. Remember, ultimately, our goal when we're doing statistics is to take what we learn or what we know about a small group. We take our small group sample, remember, which is the group that we can get information from, we can learn about, but we have to take what we learn about that sample and we have to apply it back to the population. We use what we learn about the sample to approximate the values for the population. And again, if I only have that one single estimate that I'm hedging my bets is correct, that kind of gets a little challenging. So you have the other branch of statistics is called inferential. Inferential statistics, it actually has the verb, is the adjective form of the verb to infer, which is a fancy way to say that we want to make a generalized statement. Okay, it's the idea of generalizing. So we want to make a generalization about, this is where we actually begin to apply and interpret the descriptive statistics. So the two groups or the two branches of statistics are connected because I need the descriptive statistics in order to do inferential statistics. But with inferential statistics, that's where we begin to apply and interpret the tables and the graphs and think about those point estimates. We begin to maybe make some assumptions about the data. Maybe we make the assumption that it's from a normal distribution. We begin to put our own spin on the data and what I think might be different from what Emmanuel thinks or from what Gabriella thinks. And so you get different results. Okay, but one of the things we can do with inferential statistics is, instead of using a single value for the measurement, we can begin to think about using what we call an interval estimate. Okay, an interval estimate is going to give me a range of values for the measurement, whether that measurement is the mean or the median or the standard deviation or whatever. So again, if I'm thinking about trying to hit that target, if I have a range of values that actually expands what I can hit. I don't have to worry about hitting the bullseye anymore. Maybe I have, this bigger area where I can try to aim for that bigger area. Okay, so I have a larger target than just the bullseye. So it gives me an interval or a range of values. What we call that interval of measurements, that interval of measurement is called a confidence interval. So that's where we're going to shift our focus from thinking about just an individual single value point estimate for our mean, median, mode, whatever, to thinking about an interval estimate. So I want to talk a little bit about this confidence interval. Okay, the PowerPoint that is in the course, okay, and let me see if I can get back to it. The PowerPoint that's in the course just kind of dives right in, okay, to that how to actually find those. And so I want to talk a little bit about that. Actually, I think it is actually on the PowerPoint. Maybe Miss Ralston updated it. Okay, so let's see if we can talk about confidence intervals. Okay, so a confidence interval is, again, that different type of estimate. But instead of being just a single individual value, it's going to be an interval or a group of numbers. And it gives us a range. So in terms of a range, usually you're going to have, it's going to give you a minimum. What could the possible minimum value be? And then what could the possible maximum value be? And the other word here that's important is reasonable. It gives you a range of reasonable values in which we expect our measurement, our population parameter, to fall. Okay, but again, we don't have any guarantee that the actual population parameter falls within that parameter. But what it does give me, if we calculate, as we calculate the confidence interval, we do have what they call a predictable probability of success. We can basically get a sense of how accurate, how confident are we that the population parameter falls within the interval that we have. Okay, now first of all, a couple of things I want to point out. For us, in this course, we're talking about the population parameter, which I was calling the measurement. The population parameter that we're going to focus on in this course is the mean. Okay, it's the mean. We could also talk about the variance. We could talk about the median. We could talk about the standard deviation. Okay, the mean is not the only population parameter for which we can calculate a confidence interval. It happens to be the only one that we're going to talk about. And again, what it does is we're trying to create, instead of having a single value, we're trying to create a range of values that the mean or the population mean falls into. And again, we have a predictable probability of success. We can be pretty confident. We can talk about how confident we are that we've got the right target, so to speak. That predictable probability of success is called the confidence. How confident are you that you're correct, basically, is what it boils down to. The way we create a confidence interval is you take your point estimate, like the mean, and you add or subtract the margin of error. And I messed up here a while ago. I didn't put my symbol. Okay, so we take our point estimate and then we add and subtract that margin of error. How off could our measurements be? And guys, you see this a lot in different things. For example, one summer while I was in college many years ago, I worked for a company that made ball bearings. I worked third shift, so I worked at night. And my job was to grind the bearing to a certain depth so that when they put the outer ring and the inner ring together, the balls would fit. Well, if I made the depth too much, then the balls would fall through. If I didn't make the depth deep enough, then the balls wouldn't even fit. So you had an allowance. You could be off a little bit and it would still work. Okay, so that's an example of where you might use a confidence interval because you have that allowance. You could be off by a little bit and it still work. You probably have also seen this on like anytime you see like a news report, sometimes when there's a survey. This particular graphic here is from the survey of the 2016 Republican presidential primary. And they had done a survey about, what percentage of the population were going to vote for a particular candidate. But then down here at the bottom, circled in yellow, you see this thing that says plus or minus 4.9%. Well, guys, that plus or minus 4.9% is the margin of error. That's how much these values could be off. So technically, Ted Cruz could have had between about 23% to 33% of the vote. Donald Trump would have had roughly between 21% and 31% because we're off by about plus or minus 4.9%, roughly 5%. Okay, so that's what we call the margin of error. The margin of error is how much could we be off? Margin of error is kind of the language used by everyday people. In statistics, we like to use fancy names. So in statistics, the margin of error is officially known as the error bound for the population mean, which is abbreviated EBM. Okay. So again, it's that idea of the margin of error. It is basically how much are we off? What is the allowance that you have? How much could you be off? That margin of error takes into consideration what we call the confidence level and then the adjusted standard deviation because we are applying the central limit theorem here. But Minitab is going to do all that for you behind the scenes. Okay, the confidence level is your probability of success. It is the probability that your population mean or your measurement actually falls within the given interval. In other words, it's the probability that you hit the target. It is typically stated as a percentage. And because it is a probability, remember, we learned early on that all probabilities are between and include 0 and 1. So my confidence level could actually be any value between 0 and 100%. But again, this is your probability of success. So you want your confidence to be high. So the most commonly used confidence intervals are 90%, 95%, and 99%. Now, I want to pause here for a minute. I'm going back over here to my paper for a second. Okay, so our probability of success, which basically means that I've hit the target or that I'm right, that my value for the population mean is in the interval that we've calculated, is called the confidence level. And again, it is usually stated as a percentage. The most common ones are 90%, 95%, and 99%. Of those three, the most common of those three is 95%. 95% is also what we call the default. Sometimes in research, the researcher will not state the confidence level. They let the reader decide what confidence level they want to use. And the default that is used most often, if it's not stated, is 95%. Now, I hope you realize that if there's a probability of success, meaning the probability that you're correct, you've hit the target, there is most certainly the probability that you don't. Okay, so there is the probability, get up here where I can write it down. Probability, oh, come on. Probability of failure, which means you are wrong or incorrect. The probability of failure is called the significance level. How significant is it that you're wrong? The significance level is often stated in decimal form. And it actually has a special symbol in statistics. The symbol for the significance level is the Greek letter alpha. It's the one that looks like a fish. Okay, it's the Greek letter alpha. The probability of success added to the probability of failure has to total 100%. Probability of success plus probability of failure has to total to 100%. So if my confidence level is 90%, that means that my significance level would be 10%, because 90 plus 10 is 100%. Now, as a decimal, that is 0.10. If my confidence level is 95%, my significance level is 5% because 95 plus 5 is 100. As a decimal, that's 0.05. If my confidence level is 99%, my significance level is 1% because 99 plus 1 is 100. Now, I mention this because in a few days, or actually probably a week or so, we're going to come back and we're going to talk about the significance level, because we use the significance level when we talk about hypothesis testing, which is going to be our discussion throughout modules 3 and 4. But I want you to see that the two are interconnected. Okay, so let's go back to our confidence level. Okay, so where and when do we use confidence intervals? Okay, for example, in biology, we could use a confidence interval to estimate things like the mean or the average height, weight, width, diameter of different plants or animal species. Definitely within research related to medical trials, we could use the confidence interval to determine the mean change in the blood pressure, the heart rate, the cholesterol that's related to some new drug or a new treatment. Again, we're looking at a range of values as opposed to a single individual value. And think about how useful that could be in these scenarios. Within business, in marketing and advertising, it could be used by companies to determine if a new advertising technique or some new method or some new tactic produces significantly higher revenue. Is on the average, is the revenue higher if they use a certain advertising method or a certain tactic to reach out to possible customers? Manufacturing, I mentioned to you a way that I used it, but engineers could, in manufacturing plants, determine if there's a better process, a new process to reduce the number of defective parts that are produced. Because if the parts are defective, they can't be used, and if there's too many, the company could be losing money. Okay, so that's things to think about. We ultimately will talk about 3 different confidence intervals. We're going to talk about a Z interval. We're going to talk about a T interval. And we're going to talk about a proportion. And in some cases, not for all of them, but for some of them, we can also think about how many do I need in my sample? How do researchers decide, well, I need to select 100 people, or I need to survey 50 people, or I need to survey 500 people? How do they make that determination? Now, there's various guidelines, but one guideline is based on how confident you want to be in your results. And so there's a formula or a process for determining what your sample size could or should be based on how accurate you want your results to be. Okay, so let's see if we can maybe look a little bit into Z interval, because again, we've got 3 different ones to cover, and I want us to have plenty of time to look at the 3 different ones, but also to have plenty of time to look at examples. Okay, so we're going to begin with the Z interval. Okay, if you'll notice on this kind of title page slide, it said population standard deviation is known or given. Okay, that is the number one clue that we're going to use the Z interval, is that we know or are given the population standard deviation. And again, you are going to be asked on Mini Project 2 to calculate a confidence interval. Okay, and I'll demonstrate that when we get to that point. Okay, so the Z interval, you want to kind of think about some conditions and look at the information that you're given. The conditions for conducting or using a Z interval, or really to do any confidence interval, is that you have or are using a simple random sample, which basically means every option or every item in the population had the opportunity to be selected. Nobody was favored over another. The sample size is greater than or equal to 30. Remember, that's our magic number. Or we know the distribution is normal. Because the Z interval is based on the normal distribution, which is also called the Z distribution. In these scenarios related to the confidence interval, you have to be told or be able to calculate the sample mean, the population standard deviation, the sample size, and the confidence level, which is typically stated as a percentage. Now, again, in this course, those questions are pretty much straightforward, and that information is clearly identified. There are two ways that you can see these problems. One way is you are given that summarized data. You are literally given in the scenario the sample mean, the population standard deviation, the sample size, and the confidence level. The other option is that you could be given the raw data. If you have the raw data, you still have to be told the confidence level and the population standard deviation. They may or may not tell you the sample mean or the sample size, but with the raw data, I can figure those things out because I learned way back in Module 1 how to calculate the mean, the median, the mode, the standard deviation, and so forth for my data. So I know how to do that, and Minitab does that for us. On this particular slide, and let me tell you what slide it is slide 9 on the PowerPoint for the confidence intervals for Z. On slide 9 on the PowerPoint for the confidence intervals for Z, you will find the instructions for Minitab. In the middle column, you have the steps if you have the summarized data. In the third column, you have the instructions if you have raw data. Now, in both cases, Minitab does not calculate the error bound for the population mean. It does not calculate the margin of error for you. That, again, is one of the few calculations that you will have to do manually using a calculator. It's a formula, so you're going to basically plug and chug into the formula. I believe the formula is on the next slide. The formula for the error bound for the population mean is the upper bound, your maximum, minus the lower bound, which is your minimum. Subtract them first, and then divide by 2. I hope you realize and remember from mathematics that those parentheses there imply to do this particular calculation first. Okay, so you would subtract first and then divide by 2. The biggest part of the confidence interval, because Minitab's going to do the calculations for us, is the interpretation. What does it tell us and what does it mean? The interpretation should clearly state the confidence level, explain what parameter or what measurement you are estimating, and then state the confidence interval. You have to give the lower bound as well as the upper bound. The statement that you will see me write and use is what I have in blue here. We estimate with blank % confidence. Remember, that confidence level is going to be given in the problem. We estimate with blank % confidence that the true population mean, and then you got to say mean of what? Mean age, mean number of credit hours, mean number of inches, whatever it is between the lower bound and the upper bound. And guys, we usually put the lower bound first. We always go low to high, and the upper. It's not called high, it's called upper. I'm sorry. Okay, so you'll see me write it. Now, you can get fancy with the phrasing if you want. My personal suggestion is to use this sentence here, and we will fill in the blanks. And again, I'm going to demonstrate that for you. Okay, so let me copy this. Get out of this. Hold on just a second. Let me get back to my question. This one. And I'm going to copy this and take it over to my Word document. And we'll try to go through this one example, and then we'll stop there and come back to it next week. Okay, so this one says, suppose scores on exams in statistics are normally distributed. Okay, so I'm told that I have a normal distribution with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean of 69. Find a 95% confidence interval for the true population mean of the statistic exam scores. Okay, so again, if you go back, I told you you kind of had to look for a couple of things. You wanted to make sure that you had a random sample, which it says that in the problem, and I told you it would. And then you either needed to know that it was normally distributed, or you had to have a large enough sample. So I'm good. I really don't have to worry about those 2 things, but I just wanted to point it out. Guys, the instructions tell you what you need to do, because it actually says find, or it might say construct a confidence interval. And it's giving you the confidence level. What might not be as obvious, and again, at this point, it doesn't have to be because it's the only one we've talked about. But the first thing you might really have to decide is, are you going to do a Z, a T, or a proportion? Now, we haven't talked about all three of those yet. Okay, so we only have one option. But I can rule out having using a proportion, because when I look at this, it says for the true population mean. So I can rule out proportion because this question is about a mean. So I really need to decide between Z and T. The defining factor is the fact that this problem gives me the population standard deviation, which tells me I'm going to do Z. So I'm going to find a Z interval because I know the population standard deviation. Okay, that's how I know that I'm going to do a Z interval. Then usually it's going to walk you through and ask you to identify from the problem the pieces that you need to work the problem. So it's going to ask you things like, what is the sample mean, which is X bar? It's going to ask you what is the population standard deviation, which is sigma. It's going to ask you what is the sample size, which is n, and then what is the confidence level. There's not really a symbol for confidence level. Sometimes I'll abbreviate it CL just so I don't have to write the word confidence level out every time. Guys, all four of those pieces are clearly stated in the problem. Okay, so if I go back and read, gives me a sample mean of 69. So my sample mean is 69. It says a population standard deviation of 3 points. So my population standard deviation is 3. It says a random sample of 36 scores. So my N is 36. And it says 95% confidence interval. So my confidence level is 95%. All of that is clearly given in the problem. Then usually the next 3 questions, it asks you what is the lower bound, what is the upper bound, and then what is the error bound for the population mean. The values for the upper and lower bound are going to come from Minitab. Okay, so I'm going to go over here to Minitab, and I'm going to do this calculation. Here we go. Stat. Oh, come on. Sorry, it went to sleep. I got to wake it up. Stat. Basic statistics. 1 sample Z. I have summarized data. My sample size was 36. The sample mean was 69. The known population standard deviation was 3. I go to options. We're doing a 95% confidence level, and the alternative hypothesis will always be not equal. I click OK. OK. Now, I get several pieces of information, or actually I don't. I get descriptive statistics. So here are my results. Let me copy this over to my paper so I can mark it up. Okay, it gives you your sample size. Okay, let me mark this. The N here is your sample size, which was given in the problem. You have the mean, which was given in the problem. That's the sample mean. I don't need this SE mean. And then I have 95% CI for mu. That stands for 95% confidence interval for the mean. The first number in the parentheses, and let me write this bigger, 68.020, comma, 69.980. The first number in the parentheses is your lower bound. So this number is my lower bound. That's the smallest or the minimum value that the mean could be in this problem. So my lower bound is 68.020. The second number in the parentheses is the upper bound. That is the maximum value that the mean could be in this particular problem. So my upper bound is 69.980. To find the error bound for the mean, this is a hand calculation. This is something you have to do using the formula. The formula was the upper bound minus the lower bound divided by 2. So I've got to scroll down a little bit because I've run out of space. Okay, so if I'm finding my error bound for the mean, I'm going to have my upper bound, which is 69.980, minus the lower bound of 68.020, and then I'm going to divide that by 2. We do the subtraction in the numerator first, and I know I got 4 minutes. 69.980 minus 68.020 gives me 1.96. And then I'm going to divide 1.96 by 2. So my error bound for the population mean, or my margin of error, is about 0.98 points. And then the last step, and I'm going to write this out and then we'll finish up. And we'll come back and do more of these on Monday. We estimate with 95% confidence that the true population mean score on a statistics exam is between 68.020 points and 69.980 points. Now, a couple of quick things there. One is I capitalized these words because these are important words. True population. You have to include those in your conclusion. The other spaces there, I've just filled in the blanks. I filled in the confidence level that was given. I filled in the variable. I filled in the lower bound and the upper bound. Now, I've basically run out of time, so you'll have to hold that thought on confidence intervals, and we'll come back and pick up that discussion on Monday. For now, you need to focus on the normal distribution and the application of the central limit theorem. Okay? Any questions before we go?
No questions.
I do thank you for staying even after my little issue with the power this morning. So, but we will pick up our discussion on Monday, but you do have quiz 4 and quiz 5, which are due by Sunday.
Okay.
Y'all have a good weekend.
You too. Bye.
Bye.
Bye.